All right, happy Tuesday of week 4. Yay. Okay. So, this week, today we're going to do all of chapter 6. Thursday we're doing all of chapter 7. I know that it seems quick, but we're only an 8-week term, so you're going to have test 2 next week on chapters 5, 6, and 7. So, test 2 is happening next week. It'll open Tuesday, it'll close Thursday, which means Tuesday we'll have office hours instead of a class. But see, after the test, we just have 8, 9, and 10, and they all tie really close to each other. So yes, you'll be using a little bit of new math for each one, but it builds on each other really nicely. And don't forget to send in your project proposals. There's an assignment in that final project folder. There's an assignment in there. Just type me a sentence or two. If you have a few different ideas, put all those ideas in there. Feel free to do that. I will respond and say what I think is best, and any suggestions I give you, you don't have to take. Any suggestions I give you are just basically things I think of as I'm reading your proposals. So you don't have to take them. I've had some really great projects where people didn't take my ideas, where I'm like, man, I'm really glad they didn't take that idea. So I just throw out what pops in my head, and if I was doing it with that topic, what I would do. So don't worry if you are you saying, Bradley, you saying yay about the test? I mean, I know I love a good test, but um, I don't know about others. I was really impressed with this test. It for the most part, and there were a couple of stumbles, but for the most part, it went really well. And I was super impressed with the box plots. I had fewer deductions on box plots than I've ever had. So it was really nice. I mean, there was like a couple little things here and there, but very few people tanked the box plot. So I'm very, very proud of you. Good job, everyone. And I'm looking forward to test 2. Oh, halfway through the term part. Gotcha. We're actually technically more than halfway. We're starting on the second half of the new material today because we already did chapters 1 through 5. And so now we just have chapters 6 through 10. So we're basically starting the second half of the new material today. So that part's good. So yeah, we'll get 7 on Thursday. We'll get 8 next week, and then 9 and 10 the week after that. So yeah, we're moving right along. You guys are doing fantastic. Okay, so today we're looking at chapter 6. So we're going to talk about discrete and continuous random variables. Thankfully, you already know what discrete and continuous means, so it won't be like brand new information. We're going to look at discrete probability distributions, and we're going to graph them. That is like 3 slides. It's not very much. It's going to be really quick. We're going to talk about interpreting the mean and computing it. So this mean is going to look a little bit different, and I'll explain why and what it means and all of that. And we're going to look at something called expected value, which is just another word for something we already know. So we're going to talk about expected value, what that means, and calculate a new standard deviation. And I'm going to show you some fancy schmancy calculator stuff, which will make you do a lot less hand calculation unless you like to do that. Then we're going to jump to 6.2, and we're going to talk about binomial experiments and binomial probability distributions. So I'm letting you know ahead of time that historically students kind of struggle with this section. So if you struggle with it, make sure you ask questions. And it is, for some reason, there's almost always a disconnect in this section. I'm going to do my best to be as thorough as possible, but make sure you're asking questions as you're doing the homework and to figure it out. So that's what we're doing today. We're getting through 6.2. I'm sure that you were all really happy that I canceled Lab 4. So if you didn't notice that in the email Sunday, then there you go. I canceled Lab 4. We're not going to even do it at all. I just threw it out. We will do Lab 5 later on, but I just threw out Lab 4. I really don't like Lab 4, and I haven't reworked it yet to something I like. So I just kind of threw it away. So that's where we are. That's what we're doing today. We have 46 slides. There's a few of them that we go through really quickly. We'll see. We'll see how long it takes. I don't think it'll be too bad. All right, let's get going. So a random variable. So it's basically just a numerical measure that's of an outcome of a probability. So it's just a value that's determined by chance. We use X for random variables. This is a capital X as opposed to a lowercase x. You're going to see what a random variable is in a minute. Don't worry, I'm not going to have you recount this definition to me. I don't do a lot of definition questions. I'm more of a conceptual understanding person, but sometimes it is important to have questions regarding vocabulary. So don't worry if this doesn't make any sense. You'll see what a random variable is in a minute. It's not confusing. But let's talk about discrete and continuous. So a discrete random variable. So these are qualitative or quantitative, but discrete has the number of outcomes it's something countable. It's something if I graphed it, I would graph it with dots. It would be something like um could be something like how many times a day do you check your phone? You're not going to check your phone 1.85 times per day. You're going to check your phone a discrete number of times. It will be an integer. It'll be something countable. Continuous random variable, it has an infinitely many values, just like with any continuous variable. So it's something that can take on any value. So like how many minutes or how much time passes between the times you check your phone. What is the average? Like if I pick up my phone right now and check it and put it down, then 3 seconds passed before I picked it up again. It could be 2.85 seconds. It could be 2.99 seconds. It is a continuous value, the time between counting or checking my phone again. So this is the difference, just like continuous and discrete variables. We're just throwing the random in there. And the reason that we're using random variables rather than just discrete and continuous is because with the discrete and continuous random variables, there are probabilities associated with them. You're going to see it in a second and you'll get it and you'll be like, oh yeah, that makes sense. This is cool. We got it. Don't worry. We got this. All right. So let's talk about whether these are discrete or continuous. So the number of light bulbs that burned out in a room of 10 light bulbs in the next year. I'm not going to burn out 2.35 light bulbs, so this would be discrete. It is going to be a whole number. The light bulb either burns out or it doesn't partially burn out. The number of leaves on a randomly selected oak tree. Now, this may seem like it would be continuous because it would be in the probably tens of thousands or hundreds of thousands, something like that, depends on the tree. But still, there's individual leaves, therefore this would be discrete. The length of time between 911 calls, this once again, pretty much if it's time, it is continuous. And it has to be 4 minutes and 35 seconds wait before it's 5 minutes. It has to pass through every second. Therefore, this is continuous. See, a little bit of review here, a little bit of refreshing your memory. Trying to bring back some of those brain cells that were killed trying to take that test. All right, let's move on. So a probability distribution. So we've already done something like this. Okay, so this is not something super new. So it's going to find that we have all of the possibilities of possible outcomes of a random variable X and the corresponding probabilities. So it's just like the other probability distribution tables we were making. It's all of the outcomes and the probability of it happening. Just in this case, we're using quantitative data here. So it could be a table, it could be a graph, it could be a formula, whatever, but that's a probability distribution. Once again, I'm not going to quiz you on the definition. I just want you to be able to see one and recognize it. Remember, with the probability distributions, all of the probabilities are going to add up to 1, and every value is between 0 and 1. I can tell you that with absolute certainty, on the next test, you're going to have to tell me whether something is a probability distribution. So you're going to have to tell me if it adds up to 1 and if all of the values are between 0 and 1. You will have to recognize that. So it should be easy points. All right, so this right here is a probability distribution. It is a discrete probability distribution because this asked people, then, or maybe Netflix provided the data, how many movies they streamed on Netflix each month. I mean, I guess technically you can stream a partial movie if you don't like it, but it is represented in whole numbers. So if you started streaming the movie, then you streamed the movie, apparently. So this is a probability distribution. If I added all those values together, they're going to all add up to 1. And every value is between 0 and 1. Makes sense? We okay so far? I know I'm moving fast, but this isn't like super new information. So figured moving a little fast is okay and I'll slow down when I get to the new stuff. Right. Look at that, 58% of the people only streamed one movie. It's because everybody's watching shows. Everybody's watching shows. I remember when I had Netflix 1,005 years ago, when we used to get the discs in the mail. Some of you will remember that when we used to get the discs in the mail. And I was like, I don't understand these people who watch television shows. Why are you ordering season 1 of, I don't know, Seinfeld? Pick a show. Why are you ordering these seasons of shows? Who's watching these shows? And now that's all I watch. I rarely watch movies. All I watch is shows now. It's just so weird because I used to just couldn't believe people were watching shows. Now that's what I watch. All right. Okay. So this, I already told you these rules. They all add up to 1. That's what this symbol, it just means add up to. All of the probabilities will add up to 1, and all the values will be between 0 and 1. I know I already said this 3 times, but there it is again. These are our rules. Funny thing is that summation, this right here, this right here is a sigma. We use sigma for the population standard deviation. Well, this is a capital sigma. The sigma we use for standard deviation is a lowercase sigma. So yet they're not really related. I mean, I guess kind of, because never mind, but they're not really related, but we just use the different symbols. All right. Maybe I can move on to the next page. So I'm not going to ask you to create a probability histogram. A probability histogram is basically just a relative frequency histogram. It's the exact same thing. It just has a different name. So on your vertical axis, instead of saying relative frequency, you would just put the word probability. It's the exact same thing. So here is, hold on, if I can get there. Here is my probability histogram for the number of movies streamed on Netflix. It just says probability instead of relative frequency. It is exactly the same thing. And then I'm going to show you a lazy one, a lazy probability histogram. So this one right here, this data is, we asked a basketball player to shoot free throws, and like a whole bunch of times, and they shot 3 free throws, and then we recorded how many they made. And so this right here, based on our experiment, this was the probability of making this number of shots, shooting 3 free throws. So this is called, I call it the lazy man's histogram. So it's not really a histogram. It is just graphing it so you can see what's happening. So this is not a histogram. It's just a graph. It's just a way to show discrete values. This would not work for continuous, but for discrete, it works just fine. It's not even a bar graph. It's just, I don't even know what it's called. But our textbook had it in there. That's why I took it, because it was in the textbook. And I wanted to make sure that it was represented, that it wasn't being left out, because it would be sad. So there you go. All right. Now is when I'm going to slow down, because this is new information. So I'm going to slow down. When we have a discrete random variable, we can't just add them all up and divide. I can't just add 5, 4, 3, 2, 1, 0 and divide by 6, because each value has a different probability. So renting one movie from Netflix or streaming one movie from Netflix has a 58% probability, whereas streaming zero movies from Netflix has a 6% probability. Since each one is different, when we calculate the mean, we have to weight each one. Each one has to be weighted. So we are going to use the symbol mu sub x bar. So here it is right here. Or mu sub x, not x bar, mu sub x. And then, so this is mu, and this is technically a capital X because it is the mean of our discrete random variable. So technically it should be a capital. I don't care either way. If you give me lowercase x, I'm not going to be mad. So don't worry about it. So what you do is you take each outcome and then you multiply it by the probability and you add them together. So it's going to look like this. Yes, I know multiplying by 0 just makes it 0, but I don't like to leave the 0 out because I like consistency. This will give us the mean, and I'm going to run out of room. I'm going to just add it down here. So you can put the entire thing in your calculator all at once. And you don't really have to use the parentheses if you just use the multiplication symbol. So just put them all in there and add them all together. So what I got for my mu sub x bar, or mu sub x, there's no bar, sorry. We're going to get a bar later, and that's why in my head it's just there. Mu sub x, my average is 1.49. So what this is saying is that if I kept repeating the experiment over and over and over, so I asked whenever we say many, it just means a super large number. I ask many people how many movies they stream per month from Netflix. Just ask many people. The average is going to be 1.49. It's called the law of large numbers, which as your sample size gets bigger and bigger and bigger, you're going to get closer and closer to this average. So I'm going to show you a graph of it. Whoops. And so here's the graph of it right here. So when I asked a few people, so I've got a few people up here. As I asked more and more people, I'm like averaging them every time. My average is going to approach that 1.49. So that's what it really mean is. That's what average is if you take, like when we're looking at a population average, if you take a very large number of samples, you're going to get closer and closer and closer to that population average, which we actually, most of the time, we can't poll an entire population. So you want very large numbers of samples so that we can get there. And that's the law of large numbers. I'm going to go back. All right. Any questions on calculating that probability? That's not a probability. It's a mean. Calculating that mean. I was waiting for somebody to type in the messages there, comment that messages there and be like, Gleice, you messed up your words again. All right. So this is exactly just the words that I said. Is that if I took a whole big long sample and I averaged all of them, it's going to approach that mean that we just calculated. This is called the expected value, and I'm going to get into that a little bit more in a second, but that's another word for it. It's expected value. We would expect that average to be that if we took a large sample. All right. All right. That's right here. So because it represents what we'd expect to happen in the long value, we call it the long run. It's called the expected value. The mean and the expected value are the exact same thing with a discrete random variable. It's the exact same thing. It is, we would expect our average to be this if we took a large number of samples. So I would expect if I asked many, many people how many movies they stream on Netflix every month, that average would be 1.49 based on what I know, based on what I know about the probabilities. So my mu sub, let's get a pen back on, mu sub x is the same thing as this. These are exactly the same thing. So if they ask you the mean of the discrete random variable, or they ask you the expected value, they're looking for the same thing, same math, very same math. I'm going to show you how to do it in a calculator in a minute. And I'm going to have you do it by hand first, but I'm going to show you how to do it in the calculator in a minute. All right. Okay. So a term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholders, obviously. So the premium for a 49-year-old female is $530. The payout is $250,000 if she dies. The probability that she survives a year is 0.99791. So her probability she survives is, whoa, I need a pen, 0.99791. If she survives, it costs her $530. The insurance company makes $530 if she survives. If she dies, let me calculate that probability that she dies. So it's 1 minus 0.99791. That's the probability she dies. So it's 0.00209. That's the probability that the 49-year-old woman will pass away. So it's going to cost them $250,000, but they did collect $530 from her. So I'm going to do 1 minus, I'm going to do 1, or sorry, I'm going to do 530 because that's how much money they took in, minus $250,000. So 530. So they lose $249,470. So what we're looking for is the expected value of this life insurance policy. So basically what we're saying is if they sell many, many policies, so they sell probably thousands of these policies, how much money would they expect to earn on each policy? How much money do they expect to make on every policy? Like it's averaged out over all of it. So let's calculate that. So I'm going to take this $530 and multiply it by the probability. Plus this, actually I'm going to subtract because it's a negative 249,470 times that probability. So I subtracted because that 249,470 was a negative number. So I'm going to do this, 530 times 0.99791 minus 249,470 times 0.00209. Enter. Did I calculate this correctly? I'm going to just call it $7.50 because it's 7.4979. So I'm just going to call it 750. So they're making, because based on that probability, they're making $7.50 on every policy. So if they sell many, many policies, they are expecting to make $7.50 on every policy. This is what actuaries do for a living. They determine, based on probability, they determine what should be charged for policies based on risk factors. So they're going to plug all of this stuff in and say, oh, the probability that somebody gets cancer, the probability somebody of this age dies of accidental death, all of these different things, they're going to stick those in there and they're going to calculate what is a good policy amount and based on the probability of that person surviving so that we still make money. Obviously, this relies on the law of large numbers because if I only sold 5 policies and one person died, they lost a lot of money. I'm going to go to the other page where it's prettier. There we go. So if they only sold like 5 policies and somebody dies, they lost a lot of money. But if they can sell many, many policies, they're expecting to make $750 on each policy. Questions? All right. I would like you, oh, wait, I'm going to show you. This is my Netflix example. I'm going to show you how to do this on the calculator. So take out your fancy schmancy calculator. I'm going to show you how to do this. I am going to have you do one by hand in a minute, but you can check it with your calculator. That's not the calculator. Let's go there. Okay, so here's my calculator. So go to the lists. So stat, edit. Whoa. And obviously I want to clear out my lists. You're going to need both L1 and L2. Right. In L1, you're going to put the outcomes of your discrete random variable. L2, you're going to put the probability. So take a look. So I have my probabilities in, or my outcomes of the variables in L1, probability of each one in L2. So it should look like that. And move this. Give you a second to make sure everyone has their values in there, since you can't see my data anymore. Okay. So now we're just going to go to one variable statistics for one var stats. Based on what I saw in the work on the test, most of you are doing pretty good with your one var stats. So we're going to go to stat, arrow over to calc. We want one var stats. In your list, we want L1. Frequency list, L2. Because what it's doing is it's taking L1 and it's multiplying it by L2. And then it's going to add them all together. It's doing exactly what we want it to do. So list is L1, frequency list is L2. So go ahead and do that. And I'm going to hit enter. This is exactly the mean that we got. We got 1.49 for our mean, which we better get 1.49 for our mean because we were right. We did it correctly. Questions on the calculator part, or need me to redo do it or anything? Okay, all extra quiet today. So we got the same thing. We got that 1.49. Okay, I would like you to, by hand, calculate the expected value for basketball players, then check yourself with your calculator. So do 2 things. First thing, calculate it by hand, then put it in your calculator and check yourself. Now we'll work behind you. So I would like you to be able to do it both ways. Thankfully, this is a small data set. It shouldn't take too long. How did I get 2.39 there? I think I didn't round, did I? Yeah. Did I put something in wrong? Might have. 0.01, 0.10, 0.3. Ah, I put a number in wrong. Silly me. Should be 0.39. Typo. It's amazing what happens when you put things in wrong. All right, I got 2.39. Silly me. How'd y'all do? Do okay? Questions? Anyone on the struggle bus? All right. Let's talk standard deviation. I will never, I'm not going to make you do this by hand, but I'm going to tell you how it's done. Use your calculator. So what you do is you take each data value, each variable outcome, subtract the expected value, then square it, then multiply it by the probability. No, X bar, don't use X bar. Just use mu sub X and then E of X. So don't use X bar. So just mu sub X and then E of X. Okay. So I would take every outcome minus the mean or expected value, square it, and then multiply it by the probability. Do that with each one, add them all together, and then take the square root. That's how we would calculate the standard deviation. Don't do it by hand. Don't. Use your calculator. So for example, I'm going to go back to here. I want to do both of them. So I'm going to use L3 and L4 because I just want to have all the data in here. Uh-oh. 1, 2, 3. Then I have 0 0.01, 0 0.1, 0 0.38, 0 0.51. Okay. So I'm just going to go into my 1-var stats. I'm using L3 and L4 because I put these ones in there. So the standard deviation, all it gives you is sigma. It doesn't give you a sample because this is the expected standard deviation of our entire population based on probabilities. So this right here, so my standard deviation, and we would use, clear this. Having issues. I'm going to use sigma sub X bar. Not stop the bar. I got to quit saying bar. Sigma sub X, and then it's just 0.71 approximately. So my standard deviation of my discrete random variable is about 0.71. And then we already have the mean. And I think we're not going to use that a ton. I think that your homework's just going to ask you to find it. I'm not sure what other problems are going to give you on this. I don't think that they're really going to do a whole lot about it. The variance, though, so remember that variance is just the standard deviation squared. So I'm just going to square that number. So I do 0. Can I copy and paste that? Will it let me? It won't. So 0.71, so 0.71 squared. So my variance is about 0.50. So remember, we don't really use the variance for anything. It makes us find it, but I've never used it for anything. So the variance is just the standard deviation squared. I'm going to go back to my screen here. So my standard deviation is 0.71. My variance is just that squared. It's about 0.5. So don't worry about an interpretation of the variance. Just worry about your standard deviation. Questions? All right. So Netflix data, that's not what I want to do. So our Netflix data, once again, I'm going to go back to my calculator. L1 and L2. my standard deviation. So my sigma sub x, I said it right that time. It's about 0.93. So just square that number. Squared. And then you get your variance. And that's it. Hope I didn't move too fast on that. I just didn't feel like it was super complicated since it's already in your calculator. If you need me, if you have questions or need me to go back on that, I absolutely can. Questions, comments, queries, concerns? Anyone in a quandary? So do you all watch the men's and women's gymnastics finals? I mean, oh my gosh, it was, I know that primetime tonight's going to show the women's. I watched it live this morning. It was you got to watch it. It's incredible. Just incredible. The men's also just incredible. Especially that Steve guy that yes, the pommel horse guy. Oh my gosh. Even if that's all you watch, even though there was some other really good routines that Frederick Flips, Frederick Douglass, he is really awesome. There were some great routines. So yeah, you got to watch it. There were some really great routines. Jordan Childs floor routine. Yes, Simone Biles is the GOAT, but Jordan Childs' floor routine, she has so much personality and she puts so much sass and personality into her routines. She's really amazing to watch. But yeah, you guys, you got to watch it. But yeah, watch the pommel horse guy, even if you just got to go on and just Google him and watch his video, TikTok or whatever. I've seen it probably 12 times and every time I'm in awe. But yeah, people are calling him Clark Kent because he takes the glasses off and becomes Superman on the pommel horse. He's pretty awesome. All right. I'm kind of an Olympics nerd, like from the time I was teeny tiny. I can remember watching it with my family, and so it's like nostalgic for me. All right, moving on. Sorry. Okay, we are in 6.2. Look at that. 45 minutes in, we're already in 6.2, and this is the binomial probability stuff. So there's going to be a lot of stuff in the beginning that there's some of this stuff that isn't like super requiring notes. It's like the foundational things. I will tell you the important stuff to know and what you really need to focus on. We will get there. The math is pretty much at the end. But when you are like on your test and everything is squished together rather than separated out by chapters, I know that that's part of the problem with tests is with your homework, everything is separated by sections. So you're like, I can look at my 6.2 notes and how to do these problems is going to be in the middle of, 6.2 stuff. But when you're on a test, all of the sections are squished together. So you have to dig through and figure out which thing do I use. So with a binomial probability experiment, generally your data is going to be qualitative. It's going to be like a yes or no question or a success and failure question or something. It's got your data is going to be qualitative most of the time, not 100% of the time because we're statisticians and we don't deal in absolutes. But that is what it is. So with a binomial experiment, we have to have a fixed number of trials. So the experiment is performed a fixed number of times. So you're saying something like, I'm choosing a sample size of 50 people and I'm finding out, asking them all this question, the same question. And so like, are you right-handed or left-handed? I took 50 people, so that's a fixed number of trials. 50 people, are you right-handed or left-handed? That's qualitative, and there's a fixed number of trials. The trials are independent. So the outcome of one trial cannot affect the outcome of the other trials. So they have to be independent. It can't be something like, I took one card out of a deck and I didn't put that card back. And then I took another card out of the deck because the probability of getting what I'm looking for changes if I don't put that card back in the deck. There has to be replacement there. So the trials have to be independent. So with each trial, we have to have two separate mutually exclusive outcomes, success or failure. So now there could be 20 outcomes, but I have to be looking for one specific outcome. So maybe I'm looking at hair color and I'm looking for redheads. So there can be a whole lot of different outcomes, but I'm just looking at the redhead. So a redhead would be a success and everything else would be a failure. So it just has to have a success and a failure. I'm looking for one specific thing, and then there has to be, things I'm not looking for. So it has to be one thing that gives me success. And then the last thing is that the probability doesn't change. It's a fixed probability. So a certain percent of people in the world have red hair. Therefore, there's a fixed probability of getting a redhead. It's not going to change by if I randomly choose. It's not going to be different per person. I mean, technically there is because of biology and all of that, but let's just say in the grand scheme of the world, there's a fixed probability of being a redhead. Just because that's the thing I thought of off the top of my head. So these are the things that we need to look for in order to determine if something's a binomial experiment. So you're on your test next week and you don't know what math to use. You're saying, I'm looking at this problem. I don't know what math to use. Take a look at it and say, is this categorical data that I'm looking at? Am I looking at characteristics of something or someone? Was there a fixed number of trials? Do I have like a fixed sample size? Are these independent? So if you look at these, it's going to help you to determine I need to use the binomial stuff. It's going to help you to look at that. So that would be binomial. Yeah. So I threw it 50 times. So out of 50, what is the probability? Because the probability of throwing a 6 is fixed. Yes. So you would look the probability. Well, so you have to say what how many times do you want to get so how many times do you want to get 12? So you would have to say that out of throwing the dice 50 times, what is the probability of getting 12 at exactly 3 times? So that's the kind of questions we're going to be looking at. So throwing 2 dice 50 times, what is the probability of throwing a 12 exactly 3 times? So technically, those aren't categorical, but I guess they are in this case because we're not really looking at them as like numbers. Yeah, you'll see. We'll do some examples, you'll see. So just give me a minute and you'll see how what these are going to look like. Yeah, you're on the right track though. Okay. So let's take a look at notation that we're using. So N is number of independent trials. So however many trials we have, that's a lowercase n. The P is going to be the probability of success. 1 minus P is going to be the probability of failure. So we have the probability of success is P, probability of failure 1 minus P. So my capital X is the outcome that we're looking for, or the number of successes we're looking for. So kind of like when we were back at the like the throwing the basketballs, if I'm looking for three successes, if I'm looking for him to shoot the basket and get it into the free throw, shoot a free throw 3 times out of 3, then my capital X is 3. How many successes am I looking for? That would be your capital X. Obviously, your capital X is not going to be greater than the number of trials you have. You're not going to have 4 free throws thrown if you throw the ball 3 times. Not going to happen. So these are the different notations we're looking at, N, P, and X. You're going to see the X written as capital or lowercase back and forth. Technically, it should be capital, but they look almost exactly the same, so I don't care. All right. So let's take a look at whether things are binomial experiments and why or why not. So a player rolls a pair of fair die 10 times. The number X of 7s rolled is recorded. Okay. So we have a fixed number of trials. We have a fixed number of trials. We have a fixed probability of success. However, we don't have our, where is it right here? We don't have, what am I looking for? I mean, this is not binomial. This, okay, hold on. I just lied to you, I believe. What is my brain doing here? What is my brain doing? Okay, fixed number of trials. The probability of success is the same. I rolled a fair die 10 times. Probability of success is the same. And then just it. I'm losing my mind. Trials are independent. Yes. Success and failure. Yeah. So this is binomial. Yes. I was trying to debunk it. I thought it wasn't binomial, but yeah, this is binomial because the probability of success is the same every time I roll the dice. They're mutually exclusive. So, mutually exclusive. Yes. Fixed trials. Trials. Yes. Um, probabilities, probability fixed. Yes. So yeah, it's binomial. I don't know why I was trying to debunk it. It didn't work. I could not debunk that. All right. Next. The 11 largest airlines has an on-time percentage of 84.7% in November 2001, according to this place. So we're looking for the reason for delays. So we had an FAA official select flights until she found 10 that were not on time. The number of flights X that needed to be selected is recorded. Anyone have an idea on this one? This is a no, not a fixed number of trials. It's not a fixed number of trials. The flights are independent. I mean, I guess technically, but if they're taking random flights from like, let's say the um, entire world, they're taking for, or the like entire world or entire country, the probability of them choosing them that are going to affect each other is probably pretty small. But yeah, I mean, I'm kind of iffy on whether or not they're independent because they could affect each other. But if you're looking at a large population, like all of the flights, that the probability of choosing some that affect each other is probably pretty small. But I mean, I would not mark you wrong. If you gave me that, Natalie, if you gave me that answer saying the flights are dependent, I wouldn't mark you wrong because that could be an issue also. Yeah, like the two apartment ladies, right? But because they're two ladies, like this is like two women in the entire US, not two in the same apartment complex, they're independent. So this is kind of iffy on that. I mean, I probably would have allowed this if they would have just said they chose 10 random flights rather than choosing until they found 10 that weren't on time. Because if all of them landed in at LAX, then those are clearly are dependent. So no, so you have a good point. Okay, let's move on. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. So my success is females. Is this binomial or not? Okay, this is not binomial. Does anybody have a reason why it's not binomial? So this is not binomial because they're not independent. Or basically not fixed probability. Because once I take one girl out of the class, once I take one, then there's only 29 students in the class. Then I take another one out. Or even if I choose a boy, if I take 4 students out, I take one student out. If that one's a girl, now the probability of getting a girl is going to be different in the NOS 29. If I pull the boy out, the probability is going to be different. So it's not a fixed probability of success with each one you draw out. Now, if I took 4 randomly out of 5,000 students, I would say you probably could say that's fixed probability because it's not going to change it much. Or 4 random students out of the entire world, it's going to be different. But this is not fixed probability. There's only 30 students there. All right. Questions on whether or not things are binomial. Now, I don't believe you have questions asking whether or not it's a binomial on the on your homework, but it's good to know because when you get to the test, if you don't know what to do with a problem, you're going to want to look at it and say, and check and see if this is going to be something you're going to use your binomial probability stuff with. Okay. Oh, there's another one. Nope, this is not that kind of problem. Okay. So this stuff, you do not need to write down the math that I'm going to do on the next couple of slides. I will tell you when you need to write the notes down again. I'm kind of going to explain the math behind the calculator function I'm going to give you. So you can just sit back and just look for the conceptual understanding I'm going to give you before until you need to pick up your calculator. So 7% of the people have blood type O negative. We took a simple random sample of size 4, and the number of people with blood type O negative is recorded. So I'm going to show you each of those trials. So, all right, so my first trial, I grab one person, so I have either a success or a failure. I take, or however many trials, I have a success or a failure. Second trial, I could either have a success on the first one and then success on the second one. I can go success, success. This needs to be bigger. I can have success, success, or I could have success, failure, or I can have failure, then success, or I can have failure, then failure. So you go to the third trial and it does that again. I have success, 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 or I have success, success, fail, and this goes with the fourth trial. So if I follow, let me get rid of all of this, get rid of all this stuff. So if I follow, let's say this path right here, this path right here, I have 4 successes. That's one way that my 4 trials could have gone. Then if I follow the path a little bit differently, so I follow it like this instead, I now have 3 successes. So if I follow each of these paths over, this is the different ways that the trial could have gone. There's one way that I could have had 4 successes. There's 1, 2, 3, 4 ways that I could have 3 successes. There's 1, 2, 3, 4, 5, 6 ways that I can have 2 successes. And then there's 1, 2, 3, 4 ways that I could have 1 success. One way I can have 4 successes and one way that I can have 0 successes. So knowing that there's 7% chance of getting O negative in blood, I'm going to need to calculate all of this stuff out. Take a look at what this looks like. Remember, you're not writing this down because you're not going to have to do this math. So the probability of getting 0 is the first one has to be a fail. The second one has to be a fail. These are ands. The first and the second and the third and the fourth. Since these are independent, each trial is independent, I just multiply them together. So 0.93 times 0.93 times 0.93 times 0.93. All right, that's great. So that was easy because there was just one way to do it. But I have 4 different ways that I could have 1 success. So I took 0.93 to the third power because that's, 4 ways I could have 1 success. So 0.93, that's my fail to the third power times my 1 success, but I'm multiplying it by 4 because there's 4 different ways to do this. And then there's 6 different ways to get 2. So I calculate 2 successes and multiply it by 6. So right down here, I can build my table. I can build my my distribution table right down there. Now that is a lot of work. I am not making you do this by hand. That would be a lot of work. Can you imagine if I said we were going to do 8 trials? What would that look like? I am not going to try to do one of these with 8 trials. Could you imagine how much paper you would need to do this with 8 trials? It would be outrageous. Yes, there's other math that you can do. You can do combinatorics. Some of you who've taken some higher math have probably done combinatorics before. And if you go on to Math 244, you will. And it's really fun. And I love doing it. But we're not going to do that here. I'm going straight to this is the combinatorics right here. I'm not even going to get into how to do it. Don't worry. Yeah, did you do oh, you did them all by hand every time? I'm so sorry, Natalie. I'm so sorry. Did you do combinatorics in your stats class? So, okay. We are not going to do the combinatorics. We're going straight to the calculator. This right here, this is what you write down right here. I'll show you how to use it. This is what you're writing down. So remember that the N, this right here, is the number of trials. This right here is your probability of success. And this right here is number of successes. Okay. And this is what we're using when we're looking for an exact number of successes. This is what you're writing down. We're going to do some examples. We really only have 13 slides left, y'all. Okay. Anyone need another moment? Moving on, moving on. Okay. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. So I guess technically this is quantitative and not qualitative, but we're not talking about them as if they're numbers really. We're using them as like a characteristic these houses have. So, as I said, it's not always the case, but it's helpful. In a random sample of 20 car-owning households, what is the probability that exactly 5 of those households have 3 or more cars? So we're looking for, out of those 20 car-owning households, what's the probability exactly 5 of 3 or more cars? So I'm looking for the probability that my X, my discrete random variable, equals 5. So I want to know the probability that exactly 5 of them. So that's going to look in my calculator. Don't worry, I'm going to write this down and then I'm going to show you how to do it. Binom PDF. So it's going to be, we have 20 is my sample size, 0.35 is my probability, and then 5 is the number of successes I'm looking for. So I'll let you write this down and then we'll go to the calculator. All right. Anyone need another moment? We good? Okay. Here's my calculator. I clear it just because I like a clean screen. You're going to hit the second button right here. Second. Then you're going to hit this VARS button. This button that says VARS. And it's going to give you this. I'm going to do it again. Second, VARS. Then we're scrolling down. We're going to use so many things on this screen. We're going to scroll down and it should be letter A right here, Binom PDF. And then hit enter. If yours doesn't look like this, then just put them in this order. Put the numbers in this order if yours doesn't look like this. So the number of trials is 20. The probability is 0.35. That's my probability of success. And I want exactly 5 successes. So 20 is the number of trials. That's our sample size. 0.35 is my probability of success, and I want exactly 5 outcomes. Hit enter. So this is what it would look like if you don't have that little screen that I use. This is what it's going to look like. I'm going to hit enter. So I have probability. I'm going to write it down and then I'll go back to the screen. Oops. So we have about a 12.7% chance, or 0.127 is the probability of getting exactly 5 people that have 3 or more cars. Questions on that problem? It's on my next screen. It's on my next screen. Okay, whoops, see here. Okay, before. All right. I didn't realize I had it there. Okay, I'm going to give you, you're going to get another calculator function, as long as you're okay with what we just did. What if I have something like this? So I want to know the probability that X is less than 4. So what I could do, I could do the you don't need to do this. I can do the probability X equals 1 plus the probability, X equals 0 plus the probability X equals 1 plus the probability X equals 2 plus the probability that X equals 3. I could do all of that, right? We don't want to do all that, do we? I have a calculator function that'll make it less than or equal to. So the calculator function is going to do less than or equal to. The reason I changed it to less than or equal to 3 is because I want to include the 3. Because 4 is not a an option here, right? Because it's less than 4, it means 4 is not included. 4 would not be an answer, be the right answer. But less than or equal to, so that includes 0, 1, 2, and 3. So I'm going to change it to less than or equal to 3. So I'm going to give you a new calculator function that looks very much like the other one. Binom CDF. This C right here, this C means cumulative. My number of trials is 20. My probability is 0.35. Then I'm doing 3 or fewer because it's less than or equal to 3. So when I'm using CDF, it's a cumulative function, which means it adds everything up until I hit 3. It's cumulative. The way that I remember it in my head is that binomial PDF is precise and CDF is cumulative. That's how I remember it in my own noggin. And I'll write that down after we do all of this. Okay, so in my calculator, I'm going to bounce over here, do second, and then hit the vars button. And it's the one right below PDF, right here. Binom CDF is B. Same thing, 20 trials, 0.35. And then I want 3 or fewer successes. So I got 0.444 basically. Because we definitely don't want to do all of those by hand. So remember, the CDF is the cumulative function. So PDF, precise, or exact. CDF is cumulative. Oops, I'm going to change that. So it's less than or equal to. It looks like a strange face, so you can change that to whatever you need to. You can write the words. I'm going to write the words. Less than. And never the twain shall meet. Questions, because we're going to combine all of these and do a few problems. Anyone need another moment? All right. Okay. So every time you see the word at least, what do we use? Every single time we use the word at least, what do we use? I think you mean compliment. Yes, every time you see the words at least, use the complement rule. Every single time you use the word at least, whoa, use the complement rule. Every single time. I can't say it enough. Okay. I do not have a function for greater than because we are looking for the probability that x is greater than or equal to 4. I don't have a function for that. All I have is a less than function or less than or equal to. I don't have a greater than or equal to. So you don't have to necessarily write this out unless it's helpful for you. But if I'm looking for 0, 1 second here, 2, 3, 4, 5, 6, 7, 8, dot, dot, dot. Okay, so I'm looking for the probability that at least 4 people have 3 or more cars. So that means all of these would be the answer, correct? Anything up there would be the answer. I don't have a function for that. But what I can do is I could find the probability that the answer is one of these and then take the complement. So what I'm going to do is I'm going to do 1 minus the probability that x is less than or equal to 3. Because what that's going to do is it's going to find this probability and then subtract it away. So I'm going to do 1 minus binom CDF 20, 0.35, 3. We already have that. Have I shown you guys the fun copy and paste in your calculator? Have I shown you that? So I'm going to do 1 minus, 1 minus, and I'm going to arrow up until this is highlighted and just hit enter and it pastes it. You can highlight up to anything. If you like made a typo up here, you could go back and change it. And I'm going to do that. So it's just the complement of this. Another way to do this is if I did 1 minus, and then you can do second vars, go down to the binom CDF, put all your stuff in, which is already in there, and then it pastes it there. The other way that you can do it is just go into your binom PDF or binom CDF, put that in, and then do 1 minus that answer. So whatever you need to do, just take 1 minus the binom CDF with 3, with the 3 or fewer. So every single time you see the words at least, you're going to use the complement rule. Now, if you need to write them out like this to try to figure out what exactly am I doing, go for it. If you need to write them out, go for it. Because sometimes it's a little bit confusing trying to figure it out. But just know if you do at least, you need to use the complement rule. The most common error is that people would include 4 in it. That's the most common error. Most common error is people do 1 minus the probability x is less than or equal to 4 rather than 3. Don't fall for it. Don't let it get you. Okay. Let's move over. There it is right there. Okay. All right. I would like you to try A, B, and C on your own and think about how you would do D. So get as far as you can. Remember that exact is PDF and cumulative is CDF. So I want you to start bare minimum, do A and B, but if you can get A, B, and C done, that's great. And then think about how you would do letter D. I'm going to work behind you. I'm going to let you get a head start, and then I'll work behind you. Okay. Whew. How'd we do? Before we get to the last one, I want to see if there's any questions. Questions, comments, queries, concerns? Anyone want to throw out an idea of what we would do with letter D? It's okay if you don't, it's okay. So what we're looking for is the probability that 5 is less than or equal to x is less than or equal to 7. That's what we're looking for. Okay. I mean, that is absolutely a great way to do it. Yes, you can do it that way. There's another way, but that is, yes, absolutely, Natalie. What she said, for those of you just that can only see what's on video, she said to do binomial PDF, so the exact for 5, 6, and 7 and add them together. That is absolutely great. What if we had a sample size of, say, 100? And I wanted to know if the successes were between 25 and 84. You don't want to add all those together, right? I know I don't. So, I mean, that would absolutely work for small values. 100% it'll work. I'm going to draw this out here. I'm going to do dot, 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 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is as far as I'm going to go. Okay. So what I'm looking for is I want to know these right here. Okay. Now, what if I found the probability of getting this right here, and then I subtracted off the probability of this right here. So what that would look like. Now, 100%, if you want to do binom PDF 5, 6, and 7, do it. Do it. I would do binom CDF, and then I would do 20, comma 0.417, and I would do minus binom CDF EF 20, 0.414. And that would give me that probability. Let me show you. I'm going to show you what it's going to look like on the calculator here in a second. I'm going to let you write this down and then I'll show you on the calculator. And tell you guys, I taught this class for probably 3 years before I learned that the calculator can copy and paste. I'm not ashamed to say it. Whenever I learn a new trick, I try to show it to my students because it's cool. Okay, I'm going to jump to my calculator. So what I'm going to do is I'm going to go up here and I'm just going to copy this right here. And I'm going to change this to a 7. I'll hit minus. I'm going to go back up here, copy that, paste it, change it to a 4, then hit enter. Now, if I didn't already have those things in my calculator, what I could do is do second vars, go down to binom CDF, and I want this to be a 7, hit enter, paste it. Don't hit enter again. You don't, then just hit minus, because all I wanted it to do was paste it. Now go back in there, go to binom CDF, and change this to a 4, and pasted it in there. So it just pasted both in there, and then you can hit enter. And so that answer is approximately, I'm going to go the opposite direction because I ran out of room on my screen. So I got about 0.483. Questions? Did we do okay on A, B, and C? Did those make sense? Okay. I know that it all makes sense during class, but then you get to the homework and you were like, this does not make any sense now. If I could just sit next to you and just like be your emotional support person sitting there, you would do fine.
I got a different answer on my calculation.
You
I'm,
did?
yeah.
Oh, did you
So,
add them? How did you do it? Did you add them together?
so wait, it was binom CDF parentheses 20 comma 0.41 comma 7 minus binom CDF 20 comma 0.41 comma 4.
Right. Did I do it? Maybe I quite
Yeah,
possible I did it wrong.
yeah, you used your probability was 0.35 because you copied and pasted.
Oh, okay. Yes.
Oh, okay, good. I was
Okay.
like, oh,
Thank you. Okay.
no
So it
problem.
should be, man, thank you so much. Bradley, was that you saving me?
That was me.
Okay. So 0.338, is that what you got?
Yes, that's what I got.
Okay.
Thank
So
you.
I copied and pasted the wrong thing. Sorry about that, y'all. I was using the stuff I forgot that I did on my other calculator. So 0.338. All right. So now we're going to use some of this stuff. I'm going to show you standard deviation and mean, and we're going to use some of this stuff for determining if things are unusual. Maybe if I can get to that screen. We're almost done. We're on slide 40 of 46, so we're so close to done. Okay, so to find the mean or the expected value, so to find the expected value, you multiply the trial size, the number of trials times the probability. So just take n times p, take the number of trials times the probability. That will give you your expected value. It kind of makes sense because you're like, okay, if I survey 100 people and there's a 25% chance of whatever happening, how many would you expect to have that thing happen? It would be a quarter of them. It makes sense. So just take your number of trials times the probability. For standard deviation, take the number of trials times the probability of success times the probability of failure and take the square root. So these are your formulas right there. And yes, you've got to do these ones by hand. Well, I mean, you can put them in your calculator, but yeah, I don't have a fancy thing, but it's okay. So those are your formulas. Right. Anyone need another moment? We good? Okay. So according to Experian Automotive, 35% of all car owning households have 3 or more cars. So we took 400 car owning households. We want the mean and the standard deviation of the number of car owning households we would expect to have 3 or more cars. So as I said with the mean, it's just this is still mu sub x. It's just the number of trials times the probability. So you would just take 400 times 0.35. So we would expect our expected value, we would expect 140 people to have 3 or more cars. That's what we would expect. The nice thing is if you already calculated the mean, you could just multiply that mean times the number or by the probability of failure and then take the square root. But I'm going to still write it out for you. So you would take square root of 400 times 0.35 times 1 minus 0.35. I know that it is that I could just put 0.65 and I recommend you do, but every time in the past that I've done that, I have somebody go, where did the 0.65 come from? So now just default, I just do 1 minus. But in your calculator, feel free to just put the whole thing. You might need to use parentheses to keep everything under the square root symbol. My standard deviation is approximately 9.539. Did I square root it? Yep, I did. You should be able to put the whole thing in your calculator. Questions on how we calculated that?
I have a question real quick.
Yes.
I missed that. Did you say we could just take the square root of 400 times 0.65
No, so
instead of?
no, well, see, when I'm doing this myself, because this right here is NP,
Mhm.
I would just do 140 times 0.65 and then take the square root of that.
Oh, gotcha. Okay.
Yeah. But if
Perfect.
that's going to confuse you, don't do it.
Okay. Awesome. Thank
It's
you.
just I already used that little piece, so why not just use it? You know what I'm saying?
Right. Right. Most definitely. Thank
And
you.
if you showed that in your work, so if you were calculating this on a test and in your work you just took that 140 and multiplied it by 0.65 and then took the square root, I would know what you're doing. So you don't have to rewrite it out. I know what you're doing if you do that. I like some shortcuts if they make sense. Okay. Does anybody need more examples of this or are we okay? Because I can make something up. Okay. So we are looking for, most of the time when we're dealing with binomial probability distributions, we would really like them to be bell-shaped. We want them to be nice and pretty. And if they are bell-shaped, we can use the empirical rule with them. So we like it when things are bell-shaped. In order to determine if it's bell-shaped, this right here must be true. This is kind of our rule of thumb to determine if something is bell-shaped. And this is going to keep coming up, letting you know. This NP times 1 minus P. It is going to come up in every single chapter from here on out. So if NP times 1 minus P is greater than or equal to 10, then our distribution is approximately bell-shaped, and we can use the empirical rule to determine whether things are unusual. And we like the empirical rule. We like it. Well, I hope we like it because it doesn't go away. So NP times 1 minus P must be greater than or equal to 10. Now, there's a couple other rules that we're going to follow for different things, but we're going to leave that to chapter 7 or maybe chapter 8. I'm not sure. And so don't even worry about that right now. So using the empirical rule, remember that if it is bell-shaped, 95% of our observations are within 2 standard deviations of the mean. So anything outside of that is unusual. So any probability that happens less than 5% of the time is considered unusual or an outlier. So with that 5% rule, we stick with that. So if something is 4.95% chance of happening, we consider it an outlier if it's more than 2 standard deviations from the mean. So the empirical rule, it applies if NP times 1 minus P is greater than or equal to 10, right? All right, so here we already got these numbers and we like them. And this number that was under here, that number that was under there, because the square root of that is 9.54, we know that that NP times 1 minus P is greater than or equal to 10. In fact, it's like close to 100. So we're good. Because once I took the square root of it, I'm almost at 10. Okay. Let's look back at our wireless carrier, our wireless only household. So that was 41%. I wish that I would have put it on this. So 41%. So what I'm trying to determine is if I took a simple random sample of 300 households and 143 of them were wireless only, would this result be unusual? There's a couple of different ways that we can determine this. One way, even though this isn't the way that they mean for us to do it, you could do this and get, and I don't know why we just don't do this, but I think that they might be asking you for mean and standard deviation in your homework. So, what I'm calculating is what is the probability that we would get exactly 143 households out of 300? That probability, 0.003. That's less than 5%, so yes, it would be unusual. But I'm going to show you the way that they want us to do it. So I'm going to calculate the mean. So to calculate the mean, do 300 times 0.41. It was 123. So we would expect 123 of those households to be wireless only. I bet you that number's higher than 41% these days. So for standard deviation, I get 300 times 0.41 times 1 minus 0.41. What did I just do? I don't know what I just did. Oh, I know what I just did. I'm like, something weird just happened in my calculator. So I have that the standard deviation is approximately 8.52. So in order to determine if this is an outlier, I could either calculate the z-score or I can determine what two standard deviations above the mean is. So I could do 123 plus 2 times 8.52. That's not right. 123 plus 2 times 8.52. I get 140.04. Since this number right here is smaller than 143, that means 143 is outside the two standard deviations. This would be my upper boundary or upper fence. You also could calculate the z-score if you wanted to and see if the z-score is larger than 2. So there's a few different ways to do this here. I hope I didn't just confuse you by giving you more than one method. Questions, because the next example is going to be yours, I believe. Unless I just lied and there's not really an example there. Questions, comments, queries, concerns? Okay. I guess it's not there. There isn't another example. That was the last slide. I don't know where that a new slide came from. All right. So that is the last slide. That's all I have for you today. I'm hoping that I didn't bury you too deeply in knowledge that your head's spinning. Hopefully you're okay. I felt like chapter 6 built on itself pretty nicely. Personally, this is one of my favorites. I actually use this math to prove to my administration at the high school that somebody was cheating. So they took a multiple choice test and they got like 98% on it. And they told me that they literally guessed on every single answer. So I used this to calculate the probability that they would get that many correct guessing on every single answer. And it was really, really, really small. It was really small. So yeah. So if you get if you struggle, yes, you'll work through it and you'll do great. If you have questions, you know how to find me. I try to answer as quickly as possible. So I will do the best I can to answer as quickly as possible. And you got this. You totally got this. So any questions on the record, on the recording?
This might be useful for on the recording. When you
Okay.
went through the calculator function to cut and paste,
Yes.
I wasn't able to do any of those on mine.
Oh, your calculator, you can't copy and paste. You can't do the.
I can't seem to, it won't, so when I do the arrow up and down button, it doesn't let me go anywhere.
Oh, that's terrible. Okay.
No, it's mean.
So you can do the answer thing though. So like, for example, if I needed this answer, you can do 1 minus, and then if you do second and then this negative right here, it'll just
Oh, yeah.
pull it uses the previous answer. At least you could do that much.
Okay.
I'm sad that you can't do that.
You know,
So you just have to do a lot more typing, but right. Any other questions? Any for the good of the group? Okay, I'm gonna take the recording off. If I can find the button.